Okay guys, what I want to quickly do here is run through a few key concepts relating to energy and work. So in our previous modules, what we've done is we've started to describe motion. Okay, that was our kinematics. And then we started to looking at forces, the things that drive interesting changes in motion, right? So with all of those together, we can describe all types of motion, but what we're going to do now is look at things in terms of energy, right? So taking a perspective of energy versus forces is going to help us to simplify some very complex problems, but also quantify things that are not so easily quantifiable in just looking at forces, right? So everything we're going to start doing now is we're just going to start filling out our toolkit, giving us more specialized tools and a wider set of tools so that we can find the easiest way to solve problems. So starting this off, we have this idea of energy, right? So there's a lot of different types of energy that we can consider, and there are a lot of different things that we can do with energy, but we're going to start off with just the simplest, most basic type of energy that will relate most closely to what we already know, and that is kinetic energy. Kinetic energy is the energy of something that is moving, right? If I have an object and it is moving, okay, so it has mass and it's moving, it has kinetic energy, okay? And the amount of kinetic energy it has is related to this formula right here. So Ke, I'll use that to denote kinetic energy. Sometimes you'll see this written as capital T, right, or some other variable. For us, we're going to use Ke for kinetic energy. And we have here, this is 1/2 times my mass times my velocity squared. And this here, you can even see it doesn't have our little velocity marker on it, right? We're taking here just speed, and I'm going to explain to you why this is a little bit later when we talk about what the advantages of using energy instead of forces, what these advantages are. So we'll just quickly do an example, right? So I want to know what is the kinetic energy of a 2 kilogram ball that is moving at 12 meters per second. So we can do this with our formula very easily. We can say 1/2, my mass here is 2 kilograms, and my speed is 12 meters per second squared. Okay, so what this will give us is 1/2 of 2 times 12 squared. This should be my 1/2 and my 2 here will cancel each other out. Okay, 2 divided by 2 will give me 1, so that's convenient. And my 12 squared will give me 144. So I should have 144 here. Now, what are our units? Okay, for our units, what we're going to be using, if we just look at the units we have here, we have kilograms times meters per second, but this is squared, so it would be kilogram meters squared per second squared. What we're going to do is we're going to nickname this unit again, okay, and this is going to be joule. A joule is our standard unit for kinetic energy, okay? It's the nickname for kilogram meters per second squared times meters, or kilogram times meters squared per second squared, however you want to say this. It's a bit of a mouthful, so we'll just keep this as capital J for joules, okay? Now, it's fine to say that things have kinetic energy, but we are really interested in the transfer of energy. This is the important part of energy here, in the same way that objects on their own don't have interesting lives when it comes to motion. They need forces, they need external influences in order to accelerate, right? So we're going to look at the transfer of energy. One way we can do this is we can relate the change in energy of any object to something called work. So here for work, I actually do want to put a little vector symbol here. For work, I'm going to define this as my change in energy. So how does this work? Let's say I am holding a ball. okay? And then I throw this ball. So what has happened here, okay, in terms of forces is, yes, I applied a force to this ball, and now it accelerated, and now it's moving, right? But if we look at this from the perspective of energy, is I had some energy, okay? Maybe I had something for breakfast or something for lunch. Here, we're going to put sandwich went in, okay? And that sandwich gave me energy. It had some calories, right? And now I use those calories. I use that energy and I transfer it into the ball, right? By throwing it, I use my calories to give the ball energy. So what's happened here is I've changed the energy of the ball. So here, the energy of the ball has gone up. But another thing that's sort of hidden in here that we'll talk about later when we discuss conservation of energy is the energy of me and my sandwich has gone down. I used up some of this energy to give that to the ball. Okay? So this is the transfer of energy. And when we do this, when I transfer energy into an object, when anything transfers energy into another object, we can call this work. Okay? We do work. I perform some work on the ball. Now the work results in the ball having more kinetic energy. So we can still relate this because I just said that one perspective was where I applied force to this ball and it accelerated, okay? And another perspective is that I gave energy to the ball and now it has kinetic energy. We can relate these two back so that we can still use all of our previous formulas just like we did before. So we're going to do that via this formula right here. So I forgot my little vector symbol here. So I have work as whatever force I apply. In this case, I apply a force to the ball. And over what displacement do I apply it? Okay, so I apply a force over some displacement. While I'm doing that, I'm transferring energy into that object, and that's the work that I'm applying, right? So if we take this into an example here, is let's say I have a box and I push it on the ground for a certain distance, then this displacement that I've created, along with the amount of force that I applied to the box as I slid it across the ground, will tell me how much energy I transferred, right? It'll tell me either how much energy did I consume to do that, or how much energy did this box end up gaining, okay? So when we do this, there are some considerations that we need to make similar to the way we did for forces, right? So when we said the sum of all of our forces results in acceleration, well, a bunch of things might be doing work at the same time. So when I push this box, let's say to the right, you notice that if you do this on a regular box, it doesn't end with this box having a bunch of kinetic energy, okay? And then this box taking off into the sky. Those are wings on our box. Okay, so our box doesn't suddenly have all this kinetic energy and keep moving on its own once we're done pushing, right? Usually, if you're pushing a box and then you stop pushing a box, what happens? It stops, right? So what happened? Did we just violate this? I put in work, but I didn't change the energy of the box at the end, right? That is because friction was also doing work. Friction invisibly is doing work in the opposite direction. Remember, the force of friction acts opposite of you, so it's also performing some work. So it's taking away energy from the box. As you're adding it in, friction is taking it out and turning it into heat. Okay, so there can be some invisible forces here that we need to consider, or We just need to consider more things in our scenario in order to get a full picture of what's going on. Okay, but just with these two formulas right here, we can start to build an idea of energy and forces. If we want to combine them, remember, because they're both equal to work, I can get rid of work and just connect these two things equal to each other. This is like A is equal to B, A is equal to C, so B is equal to C, right? This kind of maxim that we have here. So if I want to do this, all I would say is my change in energy is equal to my force times my displacement, okay? So if I wanted to connect these two things right here. So why do we do this, okay? So it seems like I'm just adding more pieces in now when we could just keep discussing things in terms of forces and kinematics the way we have been before, right? But there's something very special about energy and kinetic energy here in general. Let's say this formula right here doesn't depend on the direction of velocity anymore. It only depends on the speed, because once you square it, that direction kind of goes away, right? So we'll talk about this more in a future lesson, but let's say I have person, oh, you know what? This person is riding on a bike, and they travel off a ramp, and let's say they come down here to the ground, and they land on the ground. Oh, they have wheels. Okay, so if we were to do this in terms of 2D motion, there would be a lot of complex parts here to deal with, right? They have an angle here. We're going to sail through there. We're gonna fall here some distance from where we started. We're going to do a bunch of stuff. Some time is going to go by. It's all going to be crazy, right? And in all of this, you have to separate your 2D vectors into X and Y and do all of this. But if we take the concept of energy, which doesn't have direction, then we can use something that we're going to discuss in the next lesson called conservation of energy, which allows us to simplify, take away the directions, right? Just say you're moving at a certain speed here, you have some kinetic energy here, you'll have some energy at the end without discussing directions at all. And when we do this, it makes these problems so much easier to work with, right? So this is going to be sort of what we're going to be covering in this module and in the next module with potential energy and conservation of energy.